Hey everyone, welcome back to Abstract Algebra 1. This will be lecture 8 of the course, and in this section we're going to discuss a concept called isomorphism. So let's go ahead and jump into it. So we'll call this section 2.6 Isomorphisms. Now we have actually seen this concept at work already. We have a couple of examples. Most recently, we were looking at permutation groups, and specifically we had an example where we pulled out the D4, the dihedral group. So D4, remember this is the dihedral group. So it's rotations and flips of a square essentially. So we saw like R0 through R270, and then we saw the diagonal flip, the off diagonal flip, the horizontal flip, and the vertical flip. Right. So this was D4, and what we saw was that this is actually the same group. D4 could be thought of as the same group as a particular subgroup of S4. So D4 was found to be the same as a particular subgroup of S4. Okay, and so we saw this. So remember, S4 is it's what was called the symmetric group. It's a permutation group on the elements 1, 2, 3, and 4, or any 4 elements. Okay. And so D4, the dihedral group, when thought of as the symmetries of the square, and this subgroup of S4 are what can be thought of as groups that are isomorphic to one another. D4 is isomorphic to this subgroup. Okay. And so this term isomorphic is going to be sort of the subject of this section. So let's go ahead and define isomorphic and isomorphism. All right, so we'll start with the definition. Okay, so we say that an isomorphism, and we will denote it with lots of different characters, but phi is very common. An isomorphism phi from a group G to a group, and we'll just write G bar. That'll be kind of the notation we will use for denoting isomorphic groups in general, G and G bar. So an isomorphism from G to G bar is a one-to-one mapping. You can think of it also as a function from G onto, very important, onto G bar. And specifically, this mapping preserves the group operation. Okay, and we'll see what that means in a second. Okay, and so really kind of the way to kind of characterize this preserving of the group operation would be to say that phi of AB, phi of AB, try one more time. Phi of AB, right, i.e. A and B are elements in G that are combined using the group operation, is equal to phi of A times phi of B. And this will be true for all A and B in the group G. Okay, so this is what we mean by an isomorphism, right? And further, we would say that G and G bar are isomorphic if such a phi exists. Right? If there's an isomorphism between G and G bar, then we say that those two groups are isomorphic. And we'll typically denote isomorphic groups using some kind of notation like this. right? So just sort of a squiggly line. They're not equal necessarily, they're isomorphic, a little different. Okay, so let's talk this definition through with kind of a visual. Let's draw a picture. I think it's really can be instructive to see what this means in sort of a schematic form. So let's say I have a group G, okay, over here, and let's say I have a group G bar over here. Now in G, I'm going to have an element A and an element B. Okay. And these elements, there'll be a third element which is equal to sort of the product of A and B, right? Or the sum, depending on the kind of group. Okay. And so the group operation would be A and B combined to form AB. Now, in G bar, so let's assume G is isomorphic to G bar. What this means is that there's going to be an equivalent element to A, an element that's equivalent to A in G bar. And we're going to call it phi of A. And there's going to be an element that's equivalent to B in G bar. We're going to call it phi of B. Right? And then just like what we see over here, there's going to be the combination of the two elements. So phi of A and phi of B times phi of B. Right? So these are all elements in here. And so again, the same exact group operation is going to apply. Now, I've tried in this drawing to represent the relative position of these elements as being the same. The idea with doing it that way is to say that, hey, look, the structure of this group G is the same as the structure of this group G bar. And that's kind of, I try to represent that by putting things in the same position. Right? And furthermore, this element here, AB, would be mapped onto phi A, phi B. Okay? And this element B will map onto phi of B. And this element A would map onto phi of A, right? And this is all just that mapping, the isomorphism itself. Okay, here the dashed lines represent the group operations. The solid lines represent the isomorphism itself, like the isomorphism translating one group into another. Okay. All right. So this is the idea with an isomorphism. You literally have two groups that are essentially the same group, right? Meaning the group operations are all identical. One can be mapped right onto the other one, right? And this is what we saw earlier, or I guess in the previous section, when we were discussing permutation groups. And we saw that actually the dihedral group D4 can be mapped directly onto a subgroup of S4, right? These eight elements have, there's a corresponding 8 elements that form a group inside of S4. Okay, and that's what we saw with that. And so those two groups, D4 and then the subgroup of S4 that corresponds to these 8 elements, are isomorphic to one another. Now, we didn't go so far as to develop a mapping, but we'll see later in this section maybe we could do that relatively easily, right? But that was our kind of maybe one of our first examples of an isomorphism. Okay, and so this is the definition of an isomorphism. It's basically a function. It's basically a function between groups that preserves the group operation. Now, to show that something is an isomorphism, you got to show kind of 3 things. You first have to show that there's a function that exists and it's one-to-one and onto, and you have to show that the function preserves the group operation. If you can do that, then you've shown that an isomorphism, such and such a function, is an isomorphism. And furthermore, you've shown that the two groups are isomorphic. Okay, we'll get into that in a moment, though. Let's talk a little bit more about this operation preserving. Now, it depends on what kind of a group you're dealing with as to how the operation preserving function works. So let's say I've got G and the operations of G. Now, we've really only talked about multiplication or addition, right? So there's a couple of different combinations. Let's also talk about G bar. Now sometimes when you map G onto G bar, they'll have the same operations, and sometimes they'll have different operations. Right? So it can look kind of like this. Your isomorphism could map multiplication onto a group that's multiplication, or it could be addition onto addition, or the isomorphism could map multiplication onto addition, or addition onto multiplication. Right? And so in each case, the preservation is a little different. You just need to be aware of the fact that this can happen. So if I have phi of AB, i.e. multiplication, A and B are multiplied in G, then the preservation needs to be phi of A, phi of B. If I have addition and addition, then it needs to look like this. Phi of A plus B equals phi of A plus phi of B. Now when they're mixed, you just have to take note of that. Phi of AB in this case would equal phi of A plus phi of B, right? So you're mapping at multiplication onto addition, so the preservation needs to look like this, right? And then down here, okay, so we just have to be aware of that and be careful of that, right? So just because two groups have different fundamental operations, one being multiplication, the other being addition, doesn't mean that they can't be isomorphic to one another. In fact, there's lots and lots of examples where this is the case. Okay. All right. So that's that. Now, one other thing to note that I didn't point out, right? And this should be obvious, but I just want to make sure it's clear that, you know, if G is isomorphic to G bar, then this is going to imply that they have the same size, and the two groups have the same size, right? The order of G will therefore be equal to the order of G bar, right? There'll be the same number of elements, right? Now, hopefully that's clear. I mean, the isomorphism is 1-to-1, so every element maps to a single element, and the size, or sorry, so the function is 1-to-1, so every element maps to a single element, and it's onto, so every element in G bar is mapped onto. So that implies that G and G bar have to have the same order. All right, so just something to note. It kind of falls out of the definition, but want to make sure that I point that out. Okay. All right, let's talk about how to show that two groups are isomorphic. It isn't always straightforward to do this. But there is kind of a general procedure that you can usually apply and get pretty good results. I mean, except in like really strange cases, right? So in general, to show that G is isomorphic to G bar, what can we do? Well, first thing we'll want to do is we're going to have to define. Remember, an isomorphic means that there exists an isomorphism. And so if an isomorphism exists, we have to find that candidate mapping. We have to define a candidate mapping and then prove that that mapping is an isomorphism. So the first thing to do is to come up with, I'll just say define, a candidate mapping. And the mapping will be from G to G bar. Okay. And so usually this isn't, well, operating from scratch, this can be sometimes challenging, but you know, I think usually if you're working on problems in textbooks, there are lots and lots of examples where a candidate function is given and you're asked to kind of show that the isomorphism, that it is in fact an isomorphism. Right, so then the second thing is once you have this phi, this candidate mapping, you need to prove first that it's 1-to-1. You got to show that it's 1-to-1. Now, how do we show that something's 1-to-1? Well, we assume that phi of A equals phi of B, and we show that that implies that A equals B. Right? A and B being elements in G. Right? And then obviously phi of A and phi of B being elements in G bar. That's how you usually do 1-to-1, and yeah, most of the time that's going to work out. Okay, and then the third item is, of course, we need one-to-one, and then we also need onto. So we have to show that phi is onto G bar. Okay, now how do we show that something's onto? Well, we have to start with a candidate in the codomain, right? So assume that little g bar is in G bar, right? And show that there exists G and G such that phi of G is equal to little g bar, right? Okay, and so these all will get you the requirements for the mapping, right? The mapping is one-to-one and onto, essentially. And then the last thing is that you need to demonstrate that phi is operation preserving. This is usually pretty straightforward. So basically all you need to show here is that phi of AB is equal to phi of A, phi of B, right? Or if the operation is addition, then phi of A plus B, right, is equal to phi of A plus phi of B. Well, there's the four options up here, right? So one of these four options will apply to your scenario, and you need to demonstrate that, right? But once you have all of those items, then you have an isomorphism, and once you have an example of an isomorphism, you have isomorphic groups. Okay, so 1, 2, and 3 I think are straightforward. These are all very straightforward. You'll have seen these in algebra, other algebra courses. You'll have seen this in just in anything that involves, anywhere you involve functions. You talk about one-to-one or onto functions, you'll have seen these. Item 4 could be new. Item 4 could be new. This is something that comes up if you've taken linear algebra and you've talked about vector spaces. You'll have seen this concept here. But even if you've taken calculus, you should have seen this in places. So like in calculus, this idea of phi of AB equals phi of A, phi of B will have come up as well, right? So for example, when you discuss limits early on in calculus, you'll see things like limit as x approaches A of f of x times g of x is equal to the limit as x approaches A of f of x times the limit as x approaches A of g of x, right? You'll have seen that. It's a similar idea, right? And it also comes up in calculus 3 when we start talking about integration. So if I have a definite integral from a to b of two functions added together, then I can break that sum apart, and it's going to be equal to the limit, or sorry, it's going to be equal to the integral from a to b of f plus the integral from a to b of g. Right, so this will be something you'll have seen as well. Right, and all this is really saying is that, look, you can combine two elements and then run the map, right? You can combine A and B first and then run the map, or you could map the elements first and then combine them, and either way you get the same result, right? That's the idea. That's what shows you that the two groups must have the same underlying structure. The operations are preserved in the mapping. So if I map one onto the other, all of the combinations will be preserved. Right, and that's what basically tells you that the groups have the same structure, though they may look different. Okay, all right, very good. So that's how you would do it high level. And let's do some examples now. Let's take a look at a couple of examples of isomorphisms and then use that sort of strategy that we just talked through to show that the groups are indeed isomorphic. So let's take, here's a great first example, I think. So let's let G, our G group, be the real numbers under addition. Okay, so the real numbers under addition. And let's let G bar be the real numbers absent 0 under multiplication. Okay. Then if these are your two groups, G is isomorphic to G bar, right? Which is to say, let's substitute this in. R under addition is isomorphic to R star under multiplication. And what's the mapping? Well, there's probably lots of mappings, but one of them, one isomorphism, is phi of x is equal to 2 to the x power. Okay. So let's see how this is actually an isomorphism. Okay, so first of all, what's our candidate? Our candidate mapping. Well, it's given in this case, right? So phi of x is equal to 2 to the x. Okay, so this is the bridge between the two groups. This is the mapping. Okay, let's show that it's 1-to-1. How can we show that it's 1-to-1? Well, remember we have to take two items from G bar, in this case this side here, and show that if they're assumed to be equal, then their corresponding elements in G must be equal. So we'll assume, we'll take 2 to the x and 2 to the y. This is certainly in R star, right? These are non-zero. Okay. Oh, R star, sorry. Okay. Then we basically have to show that if we assume, oh, well, let's assume that 2 to the x equals 2 to the y. Then we have to show that x must equal y. Well, that's really easy to show here, right? So 2 to the x equals 2 to the y. Then I can say that log base 2 of 2 to the x equals log base 2 of 2 to the y. Right? And that's gonna, right? So you can kind of think of this almost as all canceling out here, and you just have x equals y. All right, so the implication is clear. If you've got these two elements in R star equal to one another, then these two elements in R must be equal to one another, right? So there's where you get 1-to-1. Okay. Secondly, or thirdly, I guess, in this case, we need to show that the mapping phi is onto, in this case, onto R star. Okay, so how do we do this? Well, let's let y be in G bar, well, and that's R star. I kind of am moving between notations here. Hopefully you're okay with that. We'll let y be in G bar, which is R star. Then we need to show basically that there always exists some y in R, in G in R, such that y is equal to 2x. So we wish to show that there is a y in G, which is R, right? There exists some y in G such that y is equal to 2x. Okay. Well, again, this is straightforward. This is algebra, right? If y is equal to 2x, right? Well, we can use this to figure out what y needs to be, or sorry, what x needs to be. Okay. So y is in G bar, and we need to find an x. And I think I wrote that wrong. I need to find an x, not a y. Okay. And so you can just kind of solve this equation for x here. And so the log, you'd have log base 2 of y equals log base 2 of 2 to the x. And that's going to imply that log base 2 of y is equal to just x, right? So here's your candidate for x, right? you give me any y, then I just evaluate log base 2 of the y you gave me, and this is the element that maps onto y in each case. Okay, so our phi is onto. It's an onto function. It's one-to-one and onto. So the only thing left to check is that it's operation preserving. So that's the fourth step. Right, so the fourth step. Phi is operation preserving. Okay, and so all we have to do, remember there, the formula is phi AB equals phi A, phi of B, right? So we have to show that you get the same result if you combine the elements and then map, or if you map and then combine the results of the map. Right? You get the same item, you get the same answer either way. Okay, so we can do that quick. So we let x and y be two elements in G. Right, so then I'm gonna combine them first and then map. Right, and so that just tells me that I'm dealing with this. Right, and we know how exponents work, right? So that would be 2 to the x, 2 to the y, and remember the map is just phi of x equals 2 to the x, right? Right, so this is phi of x, and then this is just phi of y, isn't it? So I have phi of x times phi of y. Right, so I've shown that phi of x plus y equals phi of x, phi of y. Okay, and so that being the case, we've shown that phi is an isomorphism from R under addition to R star under multiplication. So the implication is then that those two groups, R plus and R star under multiplication, are isomorphic. Perfect. Right? And so what we've really just said is that these two groups have the exact same structure. They're the same group, just wearing different clothes. Right? Somewhat different elements and different operation, but they do the same thing. The group operations are all preserved, and basically one is just a copy of the other almost. Okay. All right, very good. Now let's take a look at another example. Let's take a look at one more example. Let's see, which one should we do here? Well, let's take a look at a couple more examples. I think these are all good. Let's let A. All right, this is an infinite. Let's let this be the infinite cyclic group generated by some number A. Let A be an infinite cyclic group. Okay. Right, so A, we could write this in symbols a little better as A to the K, all elements of the form A to the K, where K is an integer. Right, and we're obviously saying that the order of A, the group, is infinite. Then the contention here would be that this group A is isomorphic to the integers. Under addition. Okay? I'll put under addition. So what is the mapping? Well, here we're not given the mapping, but we can think of one. The most straightforward one, since K is always an integer, would be to define phi as phi of, well, to basically say that A to the K power maps to K. Okay, so that's the mapping, the candidate mapping. Okay, let's see, is this one to one? One-to-one? Well, yeah, I mean, clearly this is one-to-one. Every K maps to only a single k in z, right? So whatever this is, it only maps to k, right? If this is 10, it only maps to 10. It doesn't map to 10 and 11. This is clearly true by construction. Just the way it's defined, right? Is it onto? Yeah, also onto, right? Because a, remember we said a was equal to a to the k power such that k is an integer, right? The implication, and the fact that the order of a is infinite, the implication there is that every integer is going to be used, right? So every integer, right? All integers, right? So again, by construction, the mapping is onto. Right. Okay, so we have one-to-one, we have onto. How about does the mapping preserve operations? Well, let's see. We'll start with two elements in A. So we'll say we have a to the x and a to the y. Okay. So if we combine the elements to begin with, then we have phi to the a times to the x plus y. Right? Now the mapping phi takes the exponents and basically makes them the elements in the other group, right? Right. Well, then that is exactly equal to phi of a to the x and phi of a to the y. Right? So it's operation preserving. Okay, perfect. So that means then that this infinite cyclic group is isomorphic to the integers under addition. Okay. Now this group could also be a lot of other examples could be spun off this kind of idea here, right? We could also say that if we have some a where a to the k again is an integer, and this time the order of a is n, well, in this case, a is going to be isomorphic to the integers mod n. Right, so you get, in the finite cyclic group case, you get isomorphisms to the integers mod n. Right, this is mod n under addition, right? So you get the same thing happening, and we kind of saw that, I think, in previous sections where we may have been looking at this and said something to the effect that multiplication in the one is the same as addition in the other, right? So the two are actually the same. And I think if you go back and review, I think the cyclic groups lecture, you'll see hints of isomorphism talk in that lecture. So we didn't use that term, and we weren't explicitly looking for isomorphisms. We definitely hinted at the idea that two groups were isomorphic or equal or equivalent in some way. Okay, let's take an example of a mapping that maybe seems like it should work, but isn't. Or, well, this one doesn't really seem too much like it should work, but let's think about the mapping, we'll say phi from R plus to itself, and we'll say it, defined by phi of x equals x cubed. Okay, now this is not an isomorphism. Right, if you start going through this example, you'll see, okay, phi is 1-to-1, and it is onto, right? Because you can get negative numbers here. This is not squared, so it's cubed. So you can get all the negative numbers, all the negative real numbers, all the positive real numbers. It's also 1-to-1, but it doesn't preserve operations. It is not operation preserving. Right, so basically, if what that means is that if I try to try to do this, if I try to say that phi of x plus y, I know that that's x plus y cubed. That is not in every case equal to x cubed plus y cubed, which would be phi of x plus phi of y. Right? We need these two to be equal, but in this case they're not. Right? And then you could find lots and lots of counterexamples, infinitely many counterexamples. A simple one would be just to think about 2 plus 5. Right? So phi of 2 plus 5 would be 2 plus 5 cubed, which is obviously not equal to 2 cubed plus 5 cubed, which would be phi of 2 plus phi of 5, right? So the operations do not preserve. So these are not equal. All right, so that's just one counterexample. There's many, many counterexamples. All you need is one, though. Right? So all you need is one. All right. Very good. Okay, and then I really like this example. I think this is a remarkable example. Well, it's remarkable in the context of the ones we just looked at, because the ones we've just looked at are relatively simple. They're kind of basic algebra. Here's an example from linear algebra that I think the fact that you can show the same thing for this way more complicated linear algebra, isomorphism, as you can show with the relatively simple ones we've just looked at, it really gives you a sense for how much structure there is in between these groups and this idea of isomorphism. So in this case, let's let G equal SL2R. Now, what the heck is this group? This is the group of 2 by 2 matrices with real valued matrices, 2 by 2, and they're going to have the standard linear group, right? So they're going to have determinant equal to 1. So G is SL2R, and I'll write this as the group, i.e. the group of 2 by 2 matrices with real entries and determinant equal to 1. Okay, so kind of a complicated group, but basically 2 by 2 matrices that have when you calculate the determinant, it's equal to 1. Okay, and we're going to let M be any 2 by 2 matrix with determinant 1. Okay, and we're going to define a mapping. We're going to define a phi from G to G, right? A mapping onto it from G onto itself, and the mapping will be defined as phi, and we're going to subscript it with M because M is some 2 by 2 matrix we've chosen. And so phi of M applied to A, where A is an element in G. Well, okay, let me say that. Okay, A is some matrix in G. Then phi of A is equal to M times A times M inverse. Okay, and this will be true for all A and G. Okay, I guess I kind of set that up here. Okay, and so the question is, so basically you choose a 2 by 2 matrix M, and it just has to, the requirement is that it have a determinant of 1. And then the mapping basically says, okay, whatever M happens to be, it's a fixed M. For all A and G, the mapping just takes M times A times M inverse, right? So M is obviously invertible if it has a determinant of 1. And so in that case, this is the mapping. Now the question is phi of M an isomorphism? That's the question, and the answer is yes, and let's see why. Okay, let's go through. So the answer is yes. Why is this an isomorphism? So first of all, the candidate mapping. So is phi a function from G to itself? And so in this case, from SL to R to SL to R. So is that true? It is true. It is true. Let's see why. So the function says, A is in SL2R and M must be in SL2R as well because it's has determinant 1. It's 2 by 2 with determinant 1. And so what we need to show is that the determinant of the resulting matrix, MAM inverse, equals 1. Well, these are all matrices with a determinant of 1, so we can apply the following. We can basically break the determinant up. And you may not have seen this linear algebra. I hope you have. Otherwise, this is total nonsense to you. But if you have seen the linear algebra, you know that, oh yeah, this is indeed fine. And so the determinant of M is 1, the determinant of A is 1, the determinant of M inverse is going to be the same as the determinant of M. It's actually 1 inverse, but in that case it's the same. And so the determinant of this matrix here, MAM, is equal to 1. And so that means that MAM inverse is in SL2R as well. Okay, so it's a 2 by 2 standard linear matrix with real entries. It has a determinant of 1. Okay, so that's the first thing. So phi m was kind of given to us, but in this case we might want to make sure that it is actually a function as it says it is. It needs to go from g to g, and it does, and you can see that here. Okay, second of all, is phi as defined, is it a 1-to-1? Well, let's find out. Let's assume that phi of m of A equals phi of m of B. Right? And what we need to show is that that implies that A and B are the same matrix. So if this is true, then M inverse equals M inverse. Right? Now, these are all invertible matrices, and so I can come in here and I can say M inverse M inverse M equals M inverse M inverse M, right? These are all the identity matrices. And so I equals I, B, I. And so obviously A equals B. Okay, so it's 1-to-1. Right? So if the two images are equal, and if the fact that the images are equal imply that the elements in the domain are equal, then you have 1-to-1. Onto. Okay, is it onto? Let's let B be in G. Okay. Now we wish to show that there exists an A in G, right? We wish to show there exists A in G such that phi of m of A equals whatever this B happens to be. Well, if such an A exists, right? So let's say it like this: if such an A exists, what would it mean? Well, it would mean that M inverse equals B. Well, I mean, you can just look at this for a second and say, hey, I'm just going to do a little bit of algebra on this. Right, multiply on the right by on the left by M inverse, and let's multiply on the right by M. And what do I get? Well, I can see then that A must equal M inverse B M. Right? So such an A does exist. Perfect. Okay, so it's on to. And finally, is this mapping operation preserving? Is it operation preserving? Well, let's let A and B be in SL2R or G. Then let's just go through the exercise of applying phi to AB, right? So I guess I didn't say this earlier, but I mean, obviously the operation here is matrix multiplication, right? So phi of AB, right, would be, let's apply it, so it'd be AB M inverse, M AB M inverse. Right, now one thing we can do here is we can get a little tricky with this, right? We could say this is equal to M A, and then right between there, let's put in an M inverse M. Actually, let's be a little more thorough here. Let's say that this is equal to M times A times the identity times B times M inverse. There's no controversy there. That identity element could be written as MA. We could write M inverse M and then B M inverse, right? And so you can see where this is going. We have MA M inverse times MB M inverse, and that of course is phi of A times phi of B. Okay, so this is operation preserving. All right. That being the case, we are good. We are done. We can say that indeed this function phi is an isomorphism. Okay. All right. So these are some good examples. Kind of a nice diverse set of examples just to get you started with being able to visualize the idea of an isomorphism. Let's jump to a big theorem here. This is a big theorem in abstract algebra. It's called Cayley's theorem. Cayley's theorem. Okay, what does it say? What it says is that every group is isomorphic to a group of permutations. Every group, right? No finite, infinite. Every single group is isomorphic to a group of permutations. Okay, that's kind of a big statement. It's a big statement. It seems to be a big statement. Now, this is important for a couple of reasons. First of all, we talked about permutation groups. They're very concrete, right? I mean, we know what the permutation groups look like. They're very concrete. And so this theorem basically says that, hey, no matter how abstract or difficult to visualize your group is, it can always be represented as a permutation group, which is very concrete, right? So first reason this is important is we can represent abstract groups with concrete permutation groups. Right, you may be thinking to yourself, those permutation groups didn't seem so concrete to me, but relative to some other groups, they are actually pretty real. The other thing is more of like a historical importance. I think I mentioned earlier that these permutation groups were kind of the first thing that people, it was our first, mathematicians' first glimpse at groups in general. So group theory started with permutation groups. And then kind of out of that, there was a lot of abstraction, right? There was a lot of different ways of thinking about groups that kind of grew out of this permutation group idea. And so really Cayley's theorem provides a kind of confirmation, that our current day way of thinking about groups, the axioms, definitions, etc., is actually a correct abstraction of the much easier, earlier notion of groups just being like permutation groups. Okay, so this theorem is proof that our modern understanding is aligned with our earliest understanding, right? Because we used to think that groups were just permutation groups, and now we see that in fact that's kind of true, right? Every group is really just, isomorphic to some permutation group, right? So it's true, but it's also not true, right? Okay, perfect. Let's prove Cayley's theorem. Because it's such a big theorem, we're going to spend a minute on this, proving it. It's not too long of a proof, a little bit though. But I think it's one worth proving, and it's within our grasp. So let's prove this. Okay, so we're going to let G be any group, obviously, right? Remember, the theorem says that every group is isomorphic to a group of permutations. So we're going to let G be any group, and what we're looking for is a G bar. Okay, so we are looking for a G bar of permutations specifically. We're looking for a permutation group that's isomorphic to G. That's what we need to find. Okay. And so a candidate mapping here would be the following. For any G in G, let's define T of G, T sub G from G to G. Right, so here we're mapping G onto itself, right? We're starting with that. We're going to define this by T sub G of X, right? Plug X into this, then you get G times X, right? And this will work for all X in G, right? So really what we're doing here is we're just multiplying X by G on the left, okay? So nothing, this notation is just, we're calling it T sub G, right? But all that really means is whatever X is, multiply it by G on the left. So this is just left multiplication by G. Okay. Now, what is great here and why this is going to work out for us is that this T, so defined, is actually a permutation on the set of elements of G. It's a permutation on the set of elements of G. And we'll see this even more so in the coming lecture, but the basic idea here is that we have this function here, this mapping, is a permutation. Now remember, we talked about permutations previously, right? We said that in order for how we defined a permutation 2 lectures ago was, we said that a permutation is a mapping that is one-to-one and onto. It's a mapping from G that is one-to-one and onto itself, G, right? So recall, a permutation is a one-to-one mapping from G onto G. So one-to-one onto from G to G, right? You may recall that. Hopefully you do. So let's show that TG is a permutation. Let's show that. Okay, let's do that. Let's not just take my word for it. Let's just show that quick. Okay, so one-to-one. T sub G is one-to-one. Let's see that first. Well, those are easy to show, right? We're going to say, assume TG of X equals TG of Y. Well, what does that mean then? That means G times X equals G times Y. And then, of course, G is a group, so there's inverses for this. So G inverse G of X equals G inverse G of Y. And so, of course, that means that e of x equals e of y, and so x equals y. I kind of took the long way around there. I could have probably just jumped to the punchline there. Left cancellation, x equals y. Okay, so it's 1-to-1. What about onto? Well, let's let y be an element in G. Then, well, it's not hard to see that if you take, we're looking for an element in G that maps to y under T, right? So that element is going to be G inverse of y. Well, why is that? Well, when I evaluate this, this becomes G times G inverse of y, doesn't it? Which is G times G inverse times y, which is just E times y, which is y. Right? So given y, and given that I know the mapping T sub G, then the element that maps to y is just G inverse y. Okay, and that's fine. That's general. Right? So T sub G is 1-to-1 and onto. Okay, and so therefore it is a permutation. Okay, so we've got a permutation. All right, so let's go ahead and define our G bar candidate. Right, we'll say G bar is equal to the set of such permutations. Okay, so G bar is equal to the set of all T sub G where G is an element of G. Okay, so G bar is a group under the operation of function composition. That's what we're going to show next. G bar is a group under the function composition. Okay, we can verify this. All right, so first of all, for all G and H and G, we have this. We have this. TG, TH of x equals TG composed of TH of x, which of course, when you evaluate TH of x, you get HX. So that's TG times HX. And of course, that means you've got G of HX, right? And then of course that is, you can bring the G and H together here, associate those, and you know then that this is equal to T sub GH of X, right? Right, and so what does this show? This shows you that TG times TH equals T of GH, which is obviously in G bar. Right, so you have like a closure here. All right. Okay. Now, function composition is associative, right? So we have that automatically. Okay, so we've got the associative function, associative operation. All right, what's the identity? Well, it's just simply TE, right? Right, TE is the identity. Now, obviously, you can just see that T sub E of X is equal to E times X, which is just X, right? So that's the identity. We have inverses, right? We have inverses. If I have T of G, then T of G inverse is the inverse. Right, so T of G inverse equals T of G inverse, right? You can just expand this and you'll see, expand this and apply it to X and you'll see that that is indeed true. Okay. And so that's that. So we have closure we have associativity, we have identities, and we have inverses. So G bar is a group. Okay, so we've found a mapping. We've identified a mapping to a permutation. We've shown that collection of permutations form a group, right? And so what's left to do? Well, we need to show that there's an isomorphism, that the two are isomorphic, right? We need to show that G is isomorphic to G bar. So defined, right? Okay, let's review. Let's make sure that we understand what we've got. So for any G, what have we done? So for any G, for any group G, we've shown we can write a permutation T sub G of X equals G of X. Okay, that was what we started with, and the key here is that this is permutation. Second, we just said let's define G bar as being equal to the set of all T sub G such that G is in the group G. Right? And we showed that this is a group of permutations. Okay, so what's left to show then is that there exists some phi from G to G bar where phi is an isomorphism. Right? If we have done that, then we will have shown that for any group G there exists an isomorphism into a permutation group. Okay, and that's the theorem, isn't it? Okay, and so the isomorphism phi here is straightforward. So what is phi? It's straightforward, actually. It's straightforward. For all G and G, what do we have to do? Let's define phi of G to be equal to T sub G. Okay, that's the mapping. Right? Let's see if this is 1-to-1. Phi is 1-to-1. So phi is 1-to-1. We'll start by saying that Tg equals T of H. Right? Well, that being the case, then T of G of the identity equals T of H of the identity, which implies that G of E equals H of E, which implies that G equals H. Okay, so you got 1-to-1. All right, so that's phi is 1-to-1. Phi is onto. Let's see if phi is onto. Well, I mean, again, phi is obviously onto. Right? Obvious. Right? Because, I mean, how is it defined for all? It's kind of like the integer case, or the case with the cyclic group and the integers. For all G and G, define phi of G equals Tg, right? So every G in the group is going to be implicitly included here. Obvious by construction. Now, does it preserve operations? Does it preserve operations? It does indeed. Let's let x and y be elements of G. Then phi of xy is equal to T sub xy, right? And we know that that, of course, is Tx, T sub y, like so, right? And this is just phi of x, and that's phi of y. All right. Perfect. Okay. Okay. All right. Now, make sure you see why this is okay. Right? Spend a minute on that one. Like, actually plug in values and confirm that it does come apart like that. Okay, perfect. So So that is the proof of Cayley's theorem. It's kind of a rough version of the proof of Cayley's theorem. Now you can go through and kind of clean that up a little bit and make it a little tighter, but that's the idea behind the proof. Okay, now this permutation group that's used throughout this proof here, this guy here. Nope, sorry, not that one. The permutation group. Which one was it? Make sure I get the right. Say the right thing here. Yeah, no, it is that one. Yeah, sorry, that permutation group. Yeah. So G bar from this proof where it's T sub G, G is in G. This has a special name. It's called the left regular representation of G. Right, and we'll be using this in more detail in coming lectures. Let's actually do a concrete example where we use this left regular representation of G. Let's do an example where we kind of draw it out with that. Okay, so, and specifically, let's calculate the left regular representation of U12. Right, so recall U12 is equal to this elements 1, 5, 7, and 11, and this is just basically multiplication mod 12. Okay. Now what we're going to do here is we're going to generate all of the elements of the left regular representation of U12. And so the way we're going to do it, we'll take the elements of U12 and we're going to perform left multiplication. So taking the elements of U12 and performing left multiplication, we get the following. Right, so T1, right, so 1 is an element of U12, and so T1, and these are permutations, remember, so I'm going to represent them in like the array notation. So 1, 5, 7, 11. And so the way you can think about this is 1 times 1, this is 1 times 5, this is 1 times 7, and this is 1 times 11. Now, obviously, this is the same as 1, 5, 7, 11. Nothing changes there. What about T5? What does T5 look like? Well, again, it's 1, 5, 7, 11, and here we're going to take 5 times 1, and then 5 times 5, and then 5 times 7, and then 5 times 11. Right, and so that maps on to 5 times 1 is 5, 5 times 5 is 25, mod 12 is 1, 5 times 7 is 35, mod 12, it's 11, and 5 times 11 is 55, and mod 12, 55 mod 12 is 7. Okay, and so T5 permutes these. You get kind of these crosses. So 5 goes here, 5 and 1 switch places, and 7 and 11 switch places. What about T7? 1, 5, 7, 11. Right, so this would be 7 times 1 is 7. 7 times 5 is 35, which is 11, mod 12. 7 times 7 is 49, which would be 1 mod 12, right? 60 is divisible by 12, and so this would be 50, or 50 is divisible by 12, this is 49, so it's 1. Sorry, 48 is divisible by 12, this is 49, so it's congruent to 1. And then 7 times 11 is 77, and so that is congruent to 5, right? So that's T7. And finally, T11. Well, T11 would be 11 times 1 is just 11. 11 times 5 is 55, which is congruent to 7 mod 12. 11 times 7 is 77, which is congruent to 5 mod 12. And 11 times 11 is 121, which is congruent to 1 mod 12. Okay, so these are your 4 elements of the left regular representation of U12, right? These are the permutation group that is isomorphic to U12. Okay, so we just calculated the permutation group. Now, when we say that they're isomorphic, we've been kind of emphasizing this idea that actually isomorphic means that the groups have the same structure. It means that they have the same structure, right? And so let's talk about the Cayley tables for U12 and the left regular representation of U12. So let's first I'll just write U12, and I'll let you verify this, but it works out fine. So 1, 5, 7, 11 times 1, 5, 7, 11. And this is very easy to see. This is 1, 5, 7, 11, 5, 1, 11, 7, 7, 11, 1, 5, and 11, 7, 5, 1. Right now, all this is saying is that, you know, for example, 11 times 7 is 77, which is congruent to 5 mod 12, right? So this represents the, if you take all of these elements and you multiply them out, this is the multiplication table you get. Now, remarkably, and this is really useful for you to verify, I'll show you how to verify in a moment, the left regular representation of U12, which we just sorted out, T1, T5, T7, and T11, which we just calculated up here, T1, T5, T7, T11, these guys. When you think about combining those and putting them into a Cayley table, you get the same exact structure. So you'll get T1 here, T5, T7, T11. So T1 combined with T11 gets you T11. All right, T1 combined with T5 gets you T5. Right, maybe that's not so revolutionary. This is the identity. What about the next line would be T5, T1, T11, T7. Right, so T5 combined with T7 gets you T11. Well, 5 combined with 7 gets you 11. Right, so the multiplication tables are going to have the exact same structure. T7, T11, T1, T5, T11, T7, T5, T1. Now, how do we calculate these things? Right, so you can see obviously these all look the same, but let's confirm one. What if I want to combine T5 and T7 to get T11? How does that work? Well, let's take an example of that. Let's just show how we would want to think about that if we were doing those combinations. So consider T5 combined with T7. Okay, so basically the way you want to do this, you want to start with T7. There's different ways to notate this, but we're going to do it this way. Start with T7, which we saw was 1, 5, 7, 11 would be permuted to 7, 11, 1, 5. So we start with this and apply T5 to it. Now remember, T5 was, you had your 1, 5, 7, 11, and it became 5, 1, 11, 7, right? Just reference your previous sheet. So what T5 does is it swaps these first two, and then it swaps the second two, right? So if I have T5 applied to T7, that would be 1, 5, 7, 11, 7, 11, 1, 5, right? Right, so T5 takes the first two and swaps them, right? So I've got 1, 5, 7, 11, and instead I'm going to get 11, 7, and then it also swaps the latter two, 5, 1. Okay, 11751. So according to our Cayley table, T5 combined with T7 needs to equal T11. And let's look at what we calculate for T11. 11751. 11751. So these permutations have the exact same structure as U12. Right? So applying, combining two elements in this left representation of U12 will result in an element that corresponds to the same element in U12. So U12 has the exact same structure as U12. It's isomorphic, right? So here's an example, concrete example of a permutation group that's isomorphic to, in this case, U12. Okay. All right. I think I'm going to end this video here, and then we'll have a part B where we kind of fill in a few additional gaps. Okay. All right.